Hello students, very good morning to all of you. So in previous session we have discussed about the electronic breakdown mechanisms in liquid dielectrics when it does not contains the impurity. Afterwards we have seen the suspended particle mechanism which shows that uh, how the breakdown takes place if the liquid dielectric material consists of the solid impurities. So those impurities may be in the form of the ionic impurities or any date fibers. Okay, so we have seen that how these ionic impurities or the fiber impurities getting dissolved into the liquid dielectrics during its prolonged operation. Today we are going to touch upon the cavitation and bubble mechanism. Then we will see how the breakdown takes place due to the volume of the oil when stressed with high potential gradient. We will also see the impact of the moisture content on the dielectric strength of liquid insulation, and at last we will see the thermal mechanism. So as the name suggests, cavitation or the bubble. Okay, in other way you can see it as the cultivation. Okay, so let us move on that. Before moving to the mechanisms responsible to operate the arc avalanche, let us analyze these two graphs which shows the relationship between the breakdown stress and the partial pressure of oxygen that is going to be evolved in the liquid dielectrics, and second is the characteristic between the breakdown stress and hydrostatic pressure. So ultimately these two graphs 1 and 2 represents the impact of presence of oxygen over the breakdown stress and the hydrostatic pressure of liquid on the breakdown stress. So you can observe that if the partial pressure of oxygen increases initially from 0 to, let us say, 150, 0 to 150. Okay, so there is an increase, a linear increment in the breakdown stress, okay, into this region. Okay, the further increase in the partial pressure of the oxygen that is going to be evolved in liquid dielectrics, the breakdown stress achieves the saturated region. It means it remains constant even though the partial pressure of oxygen increases. Okay, now why this is going to be happen? Because as you know that the oxygen is electronegative in nature. Okay, so because of this electronegativity nature, whatever the electrons has been emitted due to ionization of liquid under the application of heavy stress, the electrons are absorbed by the molecules and produce the negative ions. So to achieve the breakdown in those cases, it needs the higher value of the voltage. So you can see if the partial pressure of the oxygen, again we can also consider the Parson's theory, okay, Parson's law. So if we are considering the increase in the pressure, the breakdown voltage requirement is also more. Okay, so based on the electronegativity concept and based on the Parson's theory, okay, with increase in the pressure there is the linear increment in the breakdown voltage requirement or the dielectric strength. But after some time, further rise in the partial pressure will lead to the saturation to the breakdown stress. Whereas in the second case, as you can see that the hydrostatic pressure increases, again the breakdown voltage requirement increases. Okay, so ultimately if we are considering the pressure in terms of its mechanical behavior, then they will try to block the further motion in the electrons. So now as they are pushing back the electrons, so that the the kinetic energy of that electron reduces. So to achieve the breakdown, eliminate we need to eliminate the pressure, we need to eliminate the influence of that pressure, whatever the wall has been created due to this pressure, we need to eliminate it. So what it requires, it requires the tremendous kinetic energy with the electrons, and the kinetic energy of the electron depends upon the magnitude of the applied voltage. Okay, so with increase in the pressure, obviously it needs the higher value of the voltage. Okay, so this is the effect that you can observe in the liquid dielectrics by considering the two factors. One is the partial pressure of oxygen and second is the hydrostatic pressure. So let us see the cultivation and the bubble mechanism. So actually it was experimentally observed that the many liquids, the breakdown strength depends strongly upon the applied hydrostatic pressure, that what we have seen, and suggesting that a change of phase of the medium is involved in the breakdown process, which in other words means that a kind of vapor bubble formed is responsible for the breakdown. Okay, so we know that when we are applying the voltage, the current is flowing through the windings. The role of the liquid dielectric is to conduct the heat from the surface of the current carrying conductor to provide the cooling. So eventually the oil gets heated up. Okay, now as it gets heated up, there always be the vaporization. That is the one process, but it will take a longer time. If the liquid contains the impurities, then we have seen in the breakdown due to suspended particle mechanisms that uh, there might be the chance of the partial discharges if the liquid contains single impurities. Okay, so wherever the impurity is present, the electric field stress is highly developed. Okay, it is more than the corona threshold value, so it will intercept the partial discharge. So the region surrounding that partial discharge or the suspended particle gets heated up. Okay, so as a result, what happens? The vapor or the gas is being generated. So normally there are the so many reasons which are responsible to form the vapor bubbles in the liquid dielectrics when they are subjected to heavy stress, and if the and when this liquid contains the impurities. So number one is the gas pockets at the surface of the electrode. So if you suppose to recall the uh, clump mechanism theory for the breakdown, where you might have seen that one of the electrode contains the clumps which are loosely bound particles. So similarly, if you are considering your electrode, then there might be the presence of some gas pockets over its surface. So these gas pockets uh, normally gets detached, okay, when these electrostatic repulsive forces between the space charge is sufficient to overcome this surface tension. Okay, so gaseous products due to the dissociation of liquid molecules by the electron collision. So this is one of the other reason which may lead to uh, produce the vapor bubbles in liquid dielectrics, because under the application of the voltage stress there always be the ionization due to the electron collision. Okay, so this electron collision process will dissociate the liquid, and that dissociation of liquid will produce is the gaseous products. The vaporization of liquid due to corona type of discharge from the sharp points. Okay, if suppose the electrode contains some sharp point or irregular surfaces, or even when the liquid dielectric consumes the solid suspended particles, once the bubble is formed, it will gets elongated in the direction of applied field. So let us consider that suppose this is the one bubble which is present. Okay, now as it is a gaseous product, when I am giving the voltage supply, this will be elongated in the direction of the field. Okay, elongation, it means if you are taking the case of the rubber, okay, the hair rubber, okay, the rubber which is used to tie up the hair. So when you are stretching it, suppose this is the initial dimension. Now when I am stretching that rubber in both the directions, it will achieve this kind of the shape. So similar can be observed with this gaseous bubble when it gets elongated in the direction of the electric field under the influence of the electrostatic forces. So in that case the volume of the bubble remains constant during the elongation. So ultimately eventually what happens that due to this elongation of the bubble, it will breathe the gap and produce the spark. Okay, so this is how the breakdown will takes place because of this uh, presence of the gaseous bubbles. So now you can say that the breakdown occurs when the voltage drop along the length of the bubble becomes equal to the minimum value on the Parsons curve for the gas in the bubble. So this will be the condition to observe the breakdown in the liquid dielectrics when it contains the uh, gaseous bubbles. So the breakdown field, or the electric field at which the breakdown takes place, is given by this formula. E0 is equal to 1 upon epsilon 1 minus epsilon 2 into 2 pi sigma of 2 epsilon 1 plus epsilon 2 by r into pi by 4 square root of Vb upon 2r E0 minus 1 raised to 1 by 2. So where sigma represents the surface tension of the liquid, so surface tension, it means this one, that the electrostatic repulsive forces between the space charge which may be sufficient to overcome the surface tension uh, just to emit, okay, the gaseous pockets from the surface of the electrodes which were bounded strongly. So gas pockets are generally detached from the surface of electrode when its surface tensions gets eliminated due to this space charge effect. The epsilon 1 represents permittivity of the liquid, epsilon 2 represents permittivity of the gas bubble, R represents the initial radius of the bubble where the elongation is not present, and Vb represents the voltage drop in the bubble. Okay, so from this equation we can say that the breakdown strength entirely depends on the initial size of the bubble, which in turn is influenced by the hydrostatic pressure and the temperature of the liquid. So from this equation we can determine the magnitude of the electric field when the liquid possesses the bubbles. The another is the thermal mechanism. So as the name says, thermal, it means the breakdown will be followed due to the rise in the temperature. Okay, so this mechanism also explain the breakdown under the pulse condition. So actually this mechanism broadly depends upon the value of the current densities which we can observe just before the breakdown. So the high current pulses are believed to originate from the tip of microscopic projections on the cathode surface with the densities in the order of 10 raised to 3 ampere per meter cube. Okay, so if I am considering, let us say this is the cathode. Okay, this is the anode. Now suppose this cathode, this is cathode and this is anode, which are separated by the liquid dielectrics, and suppose here it contains some sharp edge. Okay, so when I am giving the voltage, the density of the current will be observed to be very large, which is in thousands of ampere per meter cube. Okay, so these high current density pulses will giving rise to the localized heating nearby the oil region. Okay, so once this oil gets heated up due to these heavy current densities, the oil gets vaporized, and once it will get vaporized, it will produce is the vapor bubbles. Okay, so generally the vapor bubbles are formed when the energy increases or energy exceeds 10 raised to 7 joules per centimeter square. So when the energy exceeds this limit, the vapor bubbles are created. So when the bubble is formed, as you know that when the bubble is formed, either it follows the breakdown due to its elongation, okay, to the critical size, or when it completely bridge the gap between the two electrodes. Okay, so normally if we suppose to consider the presence of this vapor bubble due to the localized heating of the oil, then it depends upon the uh, size of the bubble as well as the temperature of the liquid. Okay, so once the vapor gets formed or once the bubbles are produced, it may gets either elongated and bridge the gap to observe the formation of this part. So according to this mechanism, the dielectric strength of the liquid depends upon the pressure and the molecular structure of the liquid. Okay, so on both of these parameters, if you can see, okay, once the bubble gets formed, the breakdown mechanism depends upon the hydrostatic pressure and the temperature of the liquid. So in addition to that, it also depends upon the molecular structure of the liquid as well. So if we are considering the case for the n alkaline, okay, n alkanes, the breakdown strength was observed to be dependent mostly on the chain length of the molecule. Chain length, okay, chain length, it means that it's elongation. Okay, if the bubbles are produced. So if you are taking the case of n alkane, then the dielectric strength was observed to be the mostly dependent on the length of the molecule. Okay, but in case of the n alkane, uh, it is applicable at very small length, but this theory will not explain if the length of gap is more. The another is breakdown due to the moisture content. So usually you can observe the presence of the moisture in the commercial liquids. Okay, always the commercial, it means that it represents the impure liquid. So suppose we are considering the moisture content. Okay, so the maximum amount of water that could be present in the oil of good quality will be less than 50 ppm at atmospheric temperature of 30 degrees Celsius or less. Okay, so water present in the oil, as you know that it will lower down its dielectric strength. So at lower temperature, what exactly happens? The moisture gets distributed as a water globules, whereas at high temperature the water will begins to boil and produce more number of vapor bubbles. So water globules or water bubbles are the reason for the reduction of the dielectric strength of liquid insulation. Okay, so if we are drawing the characteristic, let me draw the characteristics that we can observe uh, with respect to the dielectric strength when the liquid contains the moisture. Okay, so this is y-axis and this is x-axis. Suppose on x-axis I am placing this moisture, let us m, it is in ppm, and on y-axis the breakdown voltage. So as the moisture content increases, the breakdown strength of liquid dielectric gets reduced. Okay, so in case of the gases, we have seen that up to certain extent of the moisture content, the breakdown voltage reduced with increase in the moisture level. But when the moisture content in the gas exceeds a certain limit, the breakdown voltage increases, which cannot be applied with the liquid dielectrics. If I am increasing the water content in liquid dielectrics, it will becomes more and more conductive. Okay, so in case of liquid insulations, with increase in the moisture content, the breakdown voltage reduces. The another is the stressed oil volume theory. Okay, suppose the two electrodes are there, they are separated by the liquid dielectrics. Okay, suppose this is the liquid dielectrics. Now it contains the impurities. Okay, so generally you can observe this phenomena in the commercial liquid. Okay, so in commercial liquid where the minute traces of the impurities are present, then the breakdown strength is determined by the largest possible impurity or the weak link. Okay, we can consider this impurity as a weak link. Okay, it is the weaker region. So the electrical breakdown strength of oil with these weakest impurities is defined by the weakest region in the oil. So the region which is stressed to the maximum and by the volume of oil included in that region. So according to this theory, the breakdown strength is inversely proportional to the stressed oil volume. So suppose when I am giving the potential, what exactly it means, when I am giving the voltage by keeping the other electrode as a ground, and when I am giving the voltage, the highest potential gradient is developed at the location of this cavity, or you can say the impurity. Okay, so what exactly happens? Because of this heavy potential gradient, heavy potential stress, there might be the occurrence of the partial discharges. So once the discharge takes place at the location of this impurity, the gets surrounding volume of the oil gets heated. So because of that heating, it will produces the gas. Okay, so eventually what happens, that the gases are generated. Now as the gases have a comparatively low dielectric strength compared to this liquid dielectric, the it will giving rise to the temperature of the liquid insulation. So ultimately what exactly happens, that the viscosity of the oil gets changed. So breakdown voltage is highly influenced by the gas content in the oil, viscosity of the oil, and presence of the other impurities. So this will being uniformly distributed. Whatever the gas content or gas bubbles has been created are uniformly distributed, and it will increase the stressed oil volume, consequently results in a reduction in the breakdown voltage. So normally the stressed oil volume is measured in terms of cubic centimeters. So if I am drawing the characteristic between the breakdown voltage and the stressed oil volume representing on x-axis, then it will reduces like this. Okay, in case of the characteristic for the moisture, it will be parabolic, but here you can see it is reduced like this. Okay, so this is the stressed oil volume theory. Okay, ultimately it represents the weakest regions, and the weakest regions are representing the presence of impurity. So that is the activity of the partial discharge, which successively increases the temperature. As a result, the gaseous bubbles are generated. So the dielectric strength in the presence of these impurities on the basis of stressed oil volume theory depends upon the gas content of the oil, the gas content in the oil, viscosity of the oil, and the presence of the other impurities. Okay, so whatever the gaseous bubbles has been generated, okay, they are uniformly distributed, and this uniform distribution will giving rise to the stresses on the volume of the remaining oil. So it would results in a reduction in the breakdown voltage. So to conclude this session, that we have attempt and discusses the various kind of mechanisms which are responsible for initiating the breakdown in liquid dielectrics. Okay, so whatever the theories that we have discussed will not consider the dependency of the dielectric strength on the gap length. They all are try to account for the maximum obtainable breakdown strength only. Okay, so in to explain all these theories, we have not considered the influence of the gap length as well. Okay, so breakdown voltage depends upon the nature of voltage, the mode in which the voltage is being applied, and time of its application. So during the last few years, the research work is directed on the measurement of discharge inception level in the oil and breakdown strength of the large volume of oil under the different conditions. Okay, in the next 20 years, the transformer oils, which are a derivative of petroleum crude, may be in the short supply. So we need to think upon the some other solution. Okay, because the transformer oil or the mineral oil is a petroleum byproduct. Okay, so uh, it is in very short supply, so we need to think upon the another alternative. So at present the current research is conducted on the natural esters, then the mineral oil based nanofluids, where the nanoparticles are going to be dispersed with a particular concentration to achieve the good heat transfer capability, good dielectric properties, and good chemical stabilities, which may be the alternative towards the existing mineral oils. So whatever the research needs to be conducted towards this liquid dielectrics, we need to take care of we need to take care of that the any of the properties may not get reduced. Okay, if suppose I am using the nanofluids, and if suppose the nanofluid only provide me the better heat transfer capability rather than providing the better insulating property, then I cannot use it for the high voltage devices. So whatever the liquid that you are going to be designing or producing, first you have to check all the properties. If the property values are satisfying you, then it can be applied to your high voltage device. So this is all about the various kinds of breakdown mechanisms that we can observe in case of the liquid dielectrics, whether it is in a pure state or in the impure state. So thank you guys.